Welcome back, everyone. In the previous sections, we introduced one of the many classes available in the Chains module, the LLM chain class. We didn't focus on the rest of the classes because they're gradually becoming a legacy standard in place of a more intuitive, efficient, and powerful expression language. LangChain Expression Language is a way of grouping chains out of individual components, known as runnables. These components and the resulting chain support a standard set of invocation methods: invoke, stream, batch, and their asynchronous analogs. You're already familiar with the invoke method that connects one component's output with another's input, linking the components. The stream method ensures that a completion token is printed out as soon as it's generated, making the application you're building more user-friendly and responsive. The batch method, intuitively, is in control of handling more than one input. Finally, the topic of asynchronous methods, while not covered in this course, is notably accessible at no extra cost through LangChain Expression Language implementation. In this lesson, we'll create and invoke a chain with the familiar but slightly modified question: I've recently adopted a pet. Could you suggest 3 pet names? The desired output would be to have the names as the elements of a list object. All right, with that said, let's get to coding. As usual, I've prepared a notebook with much of the code pre-implemented. Let me walk you through the implementation. First, we set OpenAI's API key as an environment variable. We then continue with the imports. For this demonstration, we'll need only 3 of them: the chat-OpenAI class, the chat prompt template class, and the comma-separated list output parser class. In the next cell, I've defined a variable called list instructions, where the respective formatting instructions are stored as a string. What follows is instantiating a chat prompt template variable. We've done this quite a few times already. Now let's explore an alternative method for crafting the same template as previously discussed. As usual, we create an instance of the target class, apply the FromMessages method, and set a list as an argument. Inside that list, we can define a tuple with 2 strings. The first one stores the role. In our case, that would be human. The second stores the string template: I've recently adopted a pet. Could you suggest 3 pet names? Follow the sentence with a new line character for later convenience. The word pet serves as an input variable the user specifies upon invoking the chain. The messages parameter, in turn, is a list storing a human message prompt template object. Notice that we didn't need to import and create an instance of this class. Conveniently, it was done for us. Next, let's append the formatting instructions to the template. Rerun the cell and extract the template parameter from the chat template object, like so. Print out the results. All right, our prompt template is ready. Next in line is the chat OpenAI object, defined just as usual. Following that is an object called list output parser, assigned an instance of the comma-separated list output parser class. And with that, we have all the components necessary to build our first expression language chain: a chat template, a chat model, and an output parser. Here comes the fun part. Let's take the chat template object and apply the invoke method, assigning the initial conditions: pet as a key to a dictionary, and dog as the corresponding value. The result is a chat prompt value object with a parameter named messages, storing the filled-in human message template as a human message object. Let's store this instance inside a variable called chat template result. Now take the chat object and invoke it with the chat template result variable assigned as an argument. The output is an AI message suggesting 3 names in the desired format, a list of comma-separated values. Store the result in a variable called chatResult. Finally, utilize the list output parser variable and apply the invoke method, setting the chat result variable as an argument. We obtained a list storing all 3 names as elements, precisely what we need. Let's now apply the same steps as a one-liner, utilizing the LangChain Expression Language. Start by defining an object called chain. First in the chain comes the chat template component. Proceed using a pipe symbol, which links elements in the expression language, to show that the template's output will be the input for the subsequent component. The next one is, of course, the chat object. Once more, follow this with a pipe symbol and append the third and final component, the list output parser variable. And there you have it. Our chain is defined in just a few keystrokes. All that's left to do is apply the invoke method on the chain object and pass the initial conditions as an argument. Namely, assign pet::dog as the only key value pair of a dictionary. As expected, we obtained a list of 3 names. Perfect! I hope you're starting to appreciate the elegance of this code. It's simple, clean, and intuitive. Moreover, it's easily traceable. Should we hit an error, we can apply the invoke method to each component, study the output, and pinpoint exactly where the code breaks. Excellent. We can discuss much more, so let's not waste any time. I'll see you in the next lesson to explore the batching and streaming methods. Welcome back, everyone. Last lesson, we saw how easily chains were created in the LangChain Expression Language. Recall that it uses a pipe symbol to connect components. Connecting them means that the output of one will serve as the input to the next. Additionally, we demonstrated that we can apply the invoke method to each component, allowing for transparency and traceability. In the following 2 lessons, we'll expand our toolbox and introduce 2 more methods, batch and stream. Let's get into it. As usual, let me go through the pre-implemented code I've prepared on the screen, which is quite like the one we've used in the previous lesson. We have the 2 magic commands in place. Then we import the chat prompt template and the chat OpenAI classes. Next, a chat prompt template object is defined with the familiar, but this time a slightly modified template. It includes not only the input variable pet, but also breed. I've also changed the question to, could you suggest several training tips? The following cell initializes a chat OpenAI object, and the last creates the chain by piping together the chat template with the chat object. Okay, we're all comfortable with the invoke method, but let's apply it again with the 2 input variables, pet and breed. Type chain.invoke and set a dictionary with 2 key value pairs as an argument, assigning values to the 2 input variables. I'll set the variable pet to dog and breed to shepherd. Running the cell, we see the result is an AI message with the variable content storing several valuable tips on training. But let's suppose I need training tips on more than one pet. The invoke method doesn't allow for feeding several inputs at once. Of course, we can first apply invoke with one set of input variables, and once the process is complete, apply it with another. But there's a better way to do this: batching. The batch method runs invoke in parallel, making the process less time-consuming than running several subsequent invoke methods. Let's give it a try. In a new cell, type the following: chain.batch, and as an argument, pass a list of 2 dictionaries. In the first one, the keys pet and breed are set to dog and shepherd. In the second dictionary, map the key pet to dragon and the key breed to night fury. Let's run the cell. We obtained a list of 2 AI messages. The first suggesting how to approach training a shepherd, and the second, how to train your dragon. All right, excellent so far. Let's test whether the batch method is indeed as time efficient as I've advertised. For that, let's assign 1 cell for batching both inputs together, 1 for invoking the chain with the first set of variables, and one for invoking it with the second set. If the batch method genuinely executes queries concurrently, we anticipate its execution time to be shorter than the sum of the sequential invoke statements. To calculate it, we'll use IPython's time magic command. To do so, write 2 %, followed by time before each of the 3 statements. You can read more about this magic command in IPython's documentation. You're also free to research the difference between line and cell magics, represented by 1 and 2 % respectively. Now, run the 3 cells. We anticipate an extended completion time, so I'll edit the recording to arrive at the most engaging part. Remarkably, the batch method's wall time is less than the combined wall times of the invoke methods. Therefore, we can confidently conclude that passing several inputs at once to a batch method is much more time efficient than invoking the chain that many times in sequence. You can imagine how this can scale up significantly with more dictionaries and lengthier responses. All right, I'll end our discussion on the batch method here. In the following lessons, we'll continue with the streaming process. See you shortly. Welcome back, everyone. Last lesson, we revised the invoke method and learned about its close cousin, the batch method, which allows for invoking a chain with more than a single response quickly and efficiently. We'll dedicate this lesson to the third and final method included in the expression language's standard interface, stream. Let's begin. Open the last session's notebook or a duplicate. Copy-paste either code for invoking a chain and substitute the invoke method with stream instead. Running the cell, we get an output that should look familiar. Recall that we encountered generators back when we covered OpenAI's API. Let's expand our knowledge and share additional insight into these fascinating objects. Generator functions in Python allow for defining functions that behave like iterators, allowing us to loop over their output. Unlike standard functions, generators preserve their local state, and each subsequent invocation picks up where the last one left off, instead of starting from the beginning. This is achieved through a yield statement that produces a sequence of values, instead of a return statement, which exits a function altogether. Another important property of generators is that they are single-use iterators. Once a generator has been fully iterated, it cannot be reset or reused. This constraint enhances their efficiency, notably in memory utilization, making generators ideal for tasks like streaming responses from an LLM, where handling extensive or ongoing data streams with limited memory is essential. All right, I promise this will become clearer once we implement it in code. So, let's return to our Jupyter notebook and do the following. To quickly demonstrate what happens once we iterate through all generator items, let's decrease the maximum number of completion tokens to 5. Redefine the chat and chain objects, and return to the bottom of the notebook. Store the generator object in a variable called response. To access the elements in a generator one at a time, we set it as an argument to the built-in Python function called next. Run the cell. The result is an object of type AI message chunk, simply a portion of an AI message object, storing the text in a parameter called content. Let's execute the cell several times until we exhaust all 5 tokens. Note that the content in one chunk doesn't necessarily correspond to one OpenAI token, so you might have to run the cell more than 5 times. Ultimately, we hit a stop iteration exception, signaling that the response generator has exhausted all its elements. It can no longer be used. Excellent. Now that we understand the behavior of generators, let's stream a complete response on the screen. Return to the notebook's beginning and revert the maximum completion tokens to 100. Redefine the chat and chain objects and return to the notebook's bottom. Additionally, redefine the response variable to create a new generator. In a new cell, type for_i in response. And inside the body of the for loop, prepare a print statement. Extract the content parameter from each AI message chunk object as an argument. To stream the text horizontally, add a parameter called end and set it equal to an empty string. Run the cell. And there we have it. The text is streamed just as expected when communicating with a chatbot. Great job, everyone! We've laid the foundation of the LangChain Expression Language. We learned how to pipe components to form chains and how to apply the invoke, batch, and stream methods. What follows is a technical but essential discussion on the nature of the expression language chains and their building blocks, exploring the types of objects they represent. See you in the next lesson! Hey everyone! In the last lesson, we learned how easily chains are composed using the LangChain Expression Language. Recall that this syntax uses a pipe symbol to connect components, implying that the output of one serves as the input of the next. Additionally, we demonstrated that we could apply the invoke method to each component, allowing for transparency and traceability. Of course, this is also true for the stream and batch methods. This lesson focuses on identifying the types of LangChain objects that can be integrated into a chain and the nature of the resulting chained object. On the screen, I've opened a copy of the last lesson's notebook, where I've only kept the first half of the cells, up until the initialization of the chain. Make sure you've restarted the kernel and run all cells anew. Let's examine the chain object by entering a new cell, writing type, and setting chain as an argument to this built-in Python function. We find that chain is an instance of the runnable sequence class. Peeking at the documentation, we see that this class is responsible for implementing a sequence of runnables where the output of each is the input of the next. So, each component we've appended to a chain so far, the prompt template, chat model, or output parser objects, is an instance of the runnable class. Let's now change the argument of the type function to, for example, chat template. We find it's an instance of the chat prompt template class, not the runnable class. So, how do we know this building block is, in fact, a runnable? Let's visit the documentation of the chat prompt template class. If we navigate to bases, we find that it's derived from the base chat prompt template class. Let's navigate to the class page to explore the hierarchy. We find that it's derived from the base prompt template class, which is based on the runnable serializable class. The parent classes to this last one are serializable and runnable. So, the implementation of chat prompt template starts with the runnable class, therefore inheriting the invoke, batch, and stream methods. You're encouraged to repeat this exercise with the Chat OpenAI class and any output parser classes we've covered in this previous section. Okay, so what is a runnable? Well, you already know. Referencing the documentation, a runnable is a unit of work that can be invoked, batched, streamed, transformed, and composed. Each runnable implements the invoke, batch, stream, and transform methods. Feel free to explore the transform method further in the documentation because it's beyond this course's scope. Runnables can also be composed. This refers to the property of runnables to be linked together, forming a chain. Note that the chains themselves are also runnables, and as we'll see shortly, they can also be composed to create even longer chains. Recall that the invoke method accepts different inputs based on the object applied to. Additionally, each runnable outputs a different type of object. But should we remember them all? Of course not. Instead, you can reference a convenient table from LangChain's documentation. Scroll down a bit and find the table contains 3 columns: component, input type, and output type. So, a prompt component accepts a dictionary and outputs a prompt value. A chat or a language model, in turn, accepts a prompt value and outputs a chat message or a string. An output parser transforms chat messages or strings into various formats such as strings, lists, or datetime objects. The final 2 components in the table are retriever and tool. We'll study them in the upcoming sections. I encourage you to reference this table when building your chains. It proves to be of great help, especially at the beginning of your LangChain Expression Language journey. All right, we've explored two classes within LangChain's Runnables module, the Runnable and the Runnable Sequence classes. In the next lesson, we'll continue the journey by piping together chains and introducing another class, Runnable Pass-Through. See you shortly. Welcome back, everyone. Now that we've built solid foundations on the LangChain Expression Language syntax and its inner workings, we can advance further by learning how to pipe chains together. Before that, however, we must introduce another class from the Runnables module. Open a fresh notebook and ensure you have the magic commands and the necessary imports. Additionally, I've included the Runnable Pass-Through class from the Runnables module. This class serves its intended purpose precisely as its name suggests, passing inputs through without alteration. In a new cell, create an instance of the Runnable Pass-Through class. Apply the invoke method and set any object you choose as an argument. I'll go with a simple string reading, "Hi." You can see that the output is the exact string. Let's experiment with another option, such as a list. The output is the same list with no modifications. So you can think of Runnable Pass-Through as LangChain's identity function. All right, we have all the components in place and are ready to move on with our main task, piping chains together. In the following example, we'll create a chain that lists the most essential tools for a given profession. Then, we'll feed this output to a second chain whose task will be to suggest effective strategies for mastering these tools. With the roadmap in place, let's realize it in code. Start by creating the first of two chat prompt template objects. Call it Chat Template Tools. Use the FromTemplate method instead of the FromMessages approach. As an argument, insert the string. What are the 5 most important tools a job title needs? Answer only by listing the tools. Here, job title is a placeholder for a profession the user enters. Run the cell and display the variable. Notice that, by default, this new method assumes that the template we passed as an argument is a human message prompt template. This will ease our implementation even more. In the same fashion, let's create another object called Chat Template Strategy, entering the following template. Considering the tools provided, develop a strategy for effectively learning and mastering them. Follow this with an input variable called Tools, where the list of 5 tools we previously requested will be entered. Excellent! Next, define the chat variable as we've done before. The final building block is a string output parser, which I'll name accordingly. All right, let's create 2 chains. Just as we did for the templates, let's name them based on their output. So I'll call the first one Chain Tools and pipe together the following elements: Chat Template Tools, Chat, and String Parser. In the same manner, define a chain called Chain Strategy and pipe the same elements, only changing the first component to Chat Template Strategy. Run the cell. Let's study the output of each chain separately by first invoking the Chain Tools variable with the data scientist job title. As a reminder, since we've piped a string output parser at the end of our chain, we should expect a string data type result. So let's surround this expression with parentheses and call a print function that will nicely output the string. Excellent! We see recommendations for programming languages like Python, R, SQL, visualization software, and a big data framework. Okay, I'm curious to see what strategy the model will give us. Let's invoke chain strategy by mapping tools to the output of the previous chain. For simplicity, I'll copy the result and paste it into a triple quote string. Run the cell. As expected, the chat model begins with a strategy for effectively learning Python. If we increased the maximum number of completion tokens, it would continue with a plan for each of the other 4. In fact, we can see the start of the text advising on effectively learning R. Okay, Now, how can we merge these two chains into one? Note that the first component of chain strategy accepts a dictionary with tools being the key and the value being the output from the first chain. Therefore, to connect the two chains, we must create this dictionary at the end of the first chain to input the second one. This is where the runnable pass-through class comes into play. Pipe a dictionary containing a single element at the end of the first chain. Set its key to tools, the input variable of chat template strategy, and the value to an instance of the runnable pass-through class. Let's now step back and trace the input and output of each component in chain tools. First, we call the chain with a dictionary that maps job title to data scientist. This dictionary is fed to chat template tools, which in turn outputs a chat prompt value object. This prompt value is input into the chat model, generating an AI message. The message is then assigned as an argument to the parser's invoke method. The resulting string serves as an input for the runnable pass-through. The final component mirrors its input, thereby outputting a dictionary that maps tools to the same string. Let's see if that's the case. Indeed it is. Now compare this output with the input we assigned to the invoke method in the next cell. They're precisely the same. So invoking chain strategy with the output of chain tools will connect the two runnables. Define a new chain, call it chain combined, and set it equal to chain tools piped with chain strategy. Next, invoke chain combined by setting job title to data scientist. Surround the expression with the print statement and run the cell. Very good. We obtained the beginning of an answer that suggests effective learning strategies. I hope you can see one of the significant advantages of the LangChain Expression Language, its modularity, which allows us to create these bite-sized chains and then combine them to form longer ones. Note that we can recreate the chain combined object by taking the definition of the first chain, piping it together with the definition of the second one, and thereby creating one long chain, like so. When chains start getting uncomfortably long, as has become now, you can surround them within parentheses and move the elements on a new line for better readability. All right, everyone, excellent work so far. I hope you're excited to learn more about what the LangChain Expression Language offers. The next lesson introduces a compelling way to visualize chains. Afterward, we'll continue with the topic of invoking runnables in parallel. See you soon! Welcome back, everyone! In the last lesson, we demonstrated the modularity of the LangChain Expression Language. We created two chat prompt templates. We then defined two chains by piping the respective templates with a chat model and a string parser. And finally, we employed the runnable pass-through class to prepare the output of the first chain as an input to the next one. Now, this short but valuable lesson focuses on visualizing these chains. We'll utilize a Python library that allows us to draw and understand the processes inside a chain even better. This can be especially helpful when you first encounter the LangChain Expression Language. With that said, let's begin. Open the Anaconda prompt and activate the LangChain environment. Within this environment, pip install the creatively named package, Grandalf, and wait for the installation to complete. Now return to Jupyter and either open the last lesson's notebook or create a new one with the following elements: the environment variable setup, the necessary imports, the chat prompt template objects, the chat model, the string output parser, and the definition of the chain long object. Make sure you've restarted the kernel to employ the newly installed library. Navigate to the ribbon menu, go to Cells, and select Run All. In a new one, let's apply the getGraph and then the print ASCII methods to our chain. Look at that! As promised, the chain components are nicely printed on the screen. I think we can agree that this is a straightforward chain to visualize. Throughout the course, we'll find that graphs can branch when addressing parallel processes. All right, that's it for now. We'll continue this section with an introduction to the runnable parallel class. See you in the next lesson. Welcome back, everyone. Last time we took a short break from LangChain's Runnables module and instead presented a library that allowed for visualizing chain nodes and their sequence through an ASCII print. In this lesson, we'll further unravel the magic of LangChain's expression language by demonstrating the almost magical runnable parallel class. The game plan is as follows. We'll start with 2 chains, one suggesting 3 intermediate-level programming language books, and another suggesting 3 projects on the same programming language at the same level. Both chains will accept one input, namely, the language. Contrary to previous discussions, however, our purpose won't be connecting them to form a longer chain, but instead running them simultaneously. Finally, we'll study the graph and execution time of a runnable parallel object, demonstrating a significant increase in speed compared to invoking the chains sequentially. With the strategy laid out, let's get to the implementation. Start with a fresh Jupyter notebook in the LangChain environment. I've already set up the OpenAI API key and imported the classes necessary for creating the prompt template, model, and output parser. Let's also include the runnable parallel class in the list of imports. Continue by defining 2 chat prompt template objects with the help of the fromTemplate method. Pass the following string as an argument to the first one. Suggest 3 of the best intermediate-level programming language books. Answer only by listing the books. Next, use the following string to define the second chat template. Suggest 3 interesting programming language projects suitable for intermediate-level programmers. Answer only by listing the projects. Call the top object Chat Template Books. Name the one below similarly, replacing the word books with projects. In both templates, the key phrase programming language serves as an input variable. Next, let's define the chat OpenAI and the string output parser components of the chain. Now use all 3 components to create the 2 objects, chain books and chain projects, necessary for our parallel test. Set the respective chat prompt templates we created a moment ago as the first components of each. The second component will be the chat object. Lastly, we pipe the string output parser at the end of both. Now that both chains are in place, we can construct a runnable parallel object. Create a new variable called chainParallel and set it equal to the named class. As an argument, pass a dictionary with 2 key value pairs. You can set any keys you like. I'll go with the intuitive strings books and projects. Then, the value of the first pair is set to chain books, and the value of the second pair is assigned to chain projects. Excellent! Let's continue by invoking the parallel chain. As an argument, we must map the key programming language to one of our choices. Of course, I'll go with Python. Executing the cell, there we have it. The output is a dictionary with suggested books and projects. If you've read any of these books, implemented any of these projects, or have even better recommendations, feel free to comment in the Q&A section. Let's now graph this parallel process. As before, we'll apply the getGraph and printASCII methods in sequence. Execute the command. We obtain an interesting visualization. Notice how this time the graph is split into 2. The first node represents invoking the runnable parallel object with the value Python. Then both chains' chat prompt templates are invoked in parallel. Next come the chat models, followed by the string output parsers. Finally, we obtain the result of both chains. Very good. I hope you've found this way of visualizing the chains intriguing and intuitive. it's worth noting the similarities and differences between the batch method we encountered earlier and the runnable parallel class. The batch method allowed us to invoke the same runnable with different input values. In contrast, we can execute several runnables using identical input values with the runnable parallel class. Finally, for this lesson, let's employ the time magic to compare invoking the chain parallel object and invoking chain books and projects individually. You already know the syntax, right? At the beginning of a new cell, type 2 percentage signs and follow them with the keyword time. Then invoke chain books with the Python programming language. Copy the code in the cell, enter it in a new one, and change the word books to projects. Finally, paste the same code in the third cell, and this time change the last word in the name to parallel. Execute all 3 cells and wait patiently for the output. And there we have it. We can conclusively state that invoking runnables in parallel is more time efficient than invoking them consequentially. Perfect, everyone! I hope you're excited to learn more about the runnable parallel class because we'll use it extensively throughout the course. In the next lesson of this LangChain Expression Language series, we'll pipe a runnable parallel object with another runnable into a chain. See you shortly! Welcome back, everyone! Last time, we introduced the runnable parallel class, which allows us to invoke more than one runnable at a time with the same input. We visualized the process with an ASCII graph and compared the execution times of invoking runnables in parallel and sequence, which favored the former. We'll now extend this vital discussion on runnable parallel objects by passing the books and projects from the last lesson into a new prompt template, asking for an estimate of the time it would take to complete them. So, without further ado, let's jump right in. First, open the notebook from the last lesson. Ensure you're working in the LangChain environment and clear all cell outputs to avoid cluttering the screen. The final part of the preparation would be to navigate to the bottom of the notebook and remove all cells that include the time magic. Great! Now return to the top of the file. Set up the environment variable and import all necessary classes. In the third cell of the notebook, define a new object. Call it chat template time, assign it an instance of the chat prompt template class, and apply the from template method. Pass the following template as an argument, expecting the output from the book and project chains. Based on the books from the first chain and the projects from the second, we require an estimate of their completion time. Now change the definition of the chat OpenAI object so that the maximum number of response tokens is increased to 500. This should be enough for the chat model to display the total responses from all chains. Run this and the rest of the cells to define the remaining objects in the notebook. Let's remind ourselves of what the runnable parallel object outputs. Ah yes, it's a dictionary, with books and projects as the keys of 2 key value pairs. Their corresponding values are the results of invoking chain books and chain projects. Our next task is to construct a chain that feeds this as an input to the chat template time variable. We'll define a new object called chain time. The first building block of this chain would be the chain parallel object, but rather than typing chain parallel, I'll copy and paste its definition. You'll see why in a second. Now, add the second component of this chain, the chat template time object, which will accept the dictionary from the runnable parallel instance and substitute the template's input variables with their respective strings. Next comes the chat OpenAI instance and the string output parser to retrieve the results as a string. Excellent! Enter a new cell and invoke the chain time object with a dictionary that maps programming language to Python. Wrap the result inside a print statement. the model's response roughly estimates the time necessary for completing all 3 Python books and projects. Let's see what the ASCII diagram of this chain looks like. Looks familiar, right? First, the runnable parallel is executed with the input Python. The sequences chain books and chain projects are then executed in parallel with their outputs fed to chat template time. Next come the model, the parser, and the string output. All right, I hope you find everything we've done so far intuitive and straightforward. Now go up, enter the cell defining the chain time object, and rename the object to chain time 1. Copy the code in the cell, enter a new one below to paste it, and change the number to 2. Let's apply a minor modification to the first component of the chain, retaining only the argument of the runnable parallel class. This means removing everything apart from the dictionary storing the key value pairs. Run the cell and invoke chain time 2. After a brief pause, we obtain an estimate of the workload again. Additionally, we retrieve the same ASCII diagram as before. So, what's the key takeaway here? When we pipe together a runnable parallel object with another runnable to construct a chain, we don't need to wrap the dictionary in a runnable parallel class. This is done automatically. How convenient is that? This second implementation is the one you'll encounter most often, and rightfully so because it dramatically simplifies the code. All right, everyone, excellent job. We'll pipe such runnable parallel objects as parts of chains many more times throughout this course, so you'll get to practice this further. I'll see you in the next lesson, where we'll explore another engaging topic within the same module, the runnable Lambda class. See you soon! Hey everyone! So far you've acquired much knowledge about the LangChain Expression Language and its underlying mechanism. We talked about the runnable class, implementing the invoke, batch, and stream methods. Instances of this class can be composed to create runnable sequences, also known as chains. We could also invoke several runnables simultaneously through the runnable parallel class. Another helpful class from the same module was runnable passthrough, which allows objects to be passed through the chain while keeping them unmodified. Now, we'll continue expanding our toolbox and learn how to transform ordinary functions into runnable objects. For that, we'll use Python's Lambda functions. If you need a review, please consult the final section of our intermediate Python programming course. The agenda for today's lesson is as follows. First, we'll create 2 simple Lambda functions, one that finds the sum of the elements inside a list, and one that calculates the square of a number. We'll then wrap them inside a runnable Lambda class, allowing us to call them using the invoke method. We'll then construct a simple chain from those 2 objects and graph the result. So, with that, let's get straight into coding. Open a fresh Jupyter notebook and ensure you work in the LangChain environment. Begin the implementation by creating a variable called findSum, which stores a simple Lambda function that calculates the sum of the elements inside a list. Let's test it out. In a new cell, type the function's name and enter a list as an argument. I'll populate it with elements 1, 2, and 5. Running the cell, we get the sum of these integers. Similarly, let's define a second function called findSquare. Begin with lambda x and then enter the expression x to the power of 2. Test the findSquare function by calling it with a number of your choice passed as an argument. I'll go with 8, the sum of 1, 2, and 5. The result we obtain is 64, confirming the function works properly. The functions we've just defined are great, but have one disadvantage. We can't pipe them into a chain because they aren't runnable objects and don't implement the invoke method. To remedy this, we'll need to employ the main character of this lesson, runnable lambda. Type the following: from LangChain core, .runnables, import runnable lambda. Okay, now we can create a new variable, runnable sum, and set it equal to the runnable lambda class. As an argument, I'll pass the definition of the findSum variable, namely the lambda function calculating the sum of the elements in a list. Of course, we can pass the findSum variable itself, but this will defy the purpose of lambda functions, whose primary benefit is that it can be defined without a name. Remember, they are anonymous. Run the code. To test our newly created method, let's invoke it with the same list as before, containing 1, 2, and 5. Look at that! We've seamlessly converted this lambda function to a runnable object that implements the invoke method. Let's now do the same for the second function. Define a variable called runnable square, set it equal to an instance of the runnable lambda class, and pass the second lambda function as an argument, calculating the square of a number. Next, invoke it with a number of your choice. I'll go with 8 again. Once more, we obtained the expected result. Now that we have these two runnable objects, let's pipe them together to construct a runnable sequence. Define a new variable called chain, and enter runnable sum as the first component. Follow this with a pipe symbol and insert the runnable square object as the second element. Run the cell and invoke the chain. Pass the familiar list of integers as an argument. The result is the square of the sum of these numbers, just as anticipated. Well done, everyone! Finally, for this lesson, let's investigate what the graph of this chain looks like. Recall this was done by applying the getGraph and printASCII functions sequentially. We obtain 4 components. The first one is the lambda input, namely the list of numbers. Next comes the first lambda function, which calculates the sum of these numbers. The output is fed as an input to the second runnable lambda that computes the square of the resulting sum. The final node represents the output. Excellent! I hope you can appreciate how powerful this runnable lambda class is. It allows us to convert any function into a runnable that we can then invoke and enter as a chain component. How cool is that? In the next lesson, we'll demonstrate how to create a runnable function alternatively. I'll see you shortly. Welcome back, everyone! We previously introduced LangChain's runnable lambda class, which allowed upgrading a function to a runnable object. We demonstrated this using Python's anonymous functions, but you can wrap any function this way, as we'll explain in a minute. Additionally, we'll introduce LangChain's decorators. Let's dive in. Start by opening a new Jupyter notebook in the LangChain environment. Import the familiar runnable lambda class from the runnables module. Next, define a simple function called findSum with a single parameter x, assumed to be a list. Ensure the function's body contains only return sum of x. Similarly, create another function called findSquare with a single parameter x, assumed to be a numeric value. Inside the function's body, return the square of this value. Now let's demonstrate how to create a chain using these two functions as building blocks. Define a variable chain1 as 2 instances of the runnable lambda class connected with a pipe symbol. Pass findSum as an argument to the first object and findSquare as an argument to the second. And there we have it. We've created the last lesson's example without using lambda functions. Let's test the chain with a list of numeric values to ensure it retrieves the expected result. Indeed it does. So far, so good. Now enter the cell where the two functions were defined, copy the code, and paste it into a new cell at the bottom of the notebook. To distinguish them from the functions above, rename them to runnable sum and runnable square. Return to the first cell of the notebook and add the following. From LangChain core, .runnables, import chain. Return to the cell defining the two new functions. Enter a new line above the first and type an @ symbol followed by the word chain. In Python, this construction is known as a decorator. Decorators are functions that modify the behavior of another function or a class, enhancing their functionality. Here, the chain decorator wraps the runnable sum function in a runnable lambda, just as we manually did above. Undoubtedly, creating runnables in this way is elegant and intuitive. As an added benefit, the function's name is also set as the name of the runnable. Let's do the same for the runnable square function by adding @chain before the definition. Go ahead and inspect the type of the resulting objects with the help of the type built-in function. Indeed, the objects are instances of the runnable lambda class. Excellent! Let's now create an object called chain2 and pipe runnable sum with runnable square. Invoke the chain with a list containing the elements 1, 2, and 5. As expected, the result was 64. Before I wrap up this lesson, let me insert an important remark. When using the chain decorator in your code, avoid naming your variables the same way. Doing so introduces a name conflict in the code, which could result in an error. To demonstrate, I'll restart the notebook's kernel and rename the first variable to chain. Running the cells in order, I eventually hit a type error reading, "Runnable sequence object is not callable." Remember that a Python decorator is simply a function, so what we're attempting to do in this cell is call the variable chain as if it were a Python function. But it's not. It's a runnable sequence object. All right, everyone, I'll end the lesson here. I hope you're beginning to feel comfortable with runnable lambda objects. In the rest of this section, we'll connect a memory class to a chain, practicing what we've learned and introducing several other tools along the way. Looking forward to seeing you in the next lesson. Hey everyone, and welcome back. Our ultimate goal in this series of lessons is to equip our chain with memory. In the last lesson, we prepared and combined some of the building blocks of our chain, namely the prompt template, chat model, and the string output parser. While testing our chain, however, we had to manually set the input variable message log because we had yet to attach a memory object. In this lesson, we'll introduce a convenient feature of the runnable pass-through class that'll allow the automatic completion of the message log input variable. Let's get started. Return to the second cell in the notebook and import the runnable pass-through class from the runnables module. Then ensure all variables in the notebook are defined. At the bottom of the notebook, create an instance of the runnable pass-through class. Apply the invoke method and enter a simple string. For example, hi. Recall that runnable pass-through is LangChain's analog of the identity function, so the method returns the string unmodified. In the same fashion, and integral to this lesson, passing a dictionary as an input will return the same dictionary as an output. So, let's pass a dictionary with a single key value pair, setting the key to question and the value to the familiar, "Can you give me an interesting fact I probably didn't know about?" The output is the same dictionary, as it should be. But this is only half of the information that our prompt template needs. It also requires a message log input variable that is constantly updated with the latest summary. To achieve that, we'd need to take a quick detour and study an intriguing feature of the runnable pass-through class. What follows is not difficult, but it does require 100% of your attention and then some messing around until you become entirely comfortable with the concept. Let's construct a clear, simple example. Create a runnable pass-through instance and invoke it using a dictionary with the following key value pair. Running this code outputs the same dictionary. Nothing unexpected so far. Our goal with this example is to include 2 more key value pairs in this dictionary, one keeping the first letter of the input and another keeping the second. We'll call the corresponding keys first letter and second letter. To do that, apply the class's assign method through the dot notation. Let's call our initial parameter first letter. For this example, we'll create a simple lambda function that extracts the first letter of the string. Let's do this one step at a time. To get us started, let's first type lambda x and set x as the expression for this function. we've obtained a dictionary containing a second key-value pair, with first letter as the key and the original dictionary as the value. Let's now extract only the value of this dictionary by specifying input within brackets. Excellent! Next, wrap the expression in Python's built-in list function to obtain each character as a separate element inside a list. To retrieve the first letter, extract the 0th element from the list. Marvelous! Let's now construct the third key-value pair in the same spirit. Copy-paste the lambda function we've just defined, modify the parameter's name to second letter, and change the index from 0 to 1. Very good! We've successfully expanded our dictionary. I hope the idea behind the assign method is starting to become apparent. It allows us to include additional keys to the dictionary we're passing through. This is achieved by providing the names of the keys as parameters and runnable or callable objects as their corresponding values. Okay, this is the end of our detour. Let's now return to the initial problem, which was to introduce an additional key-value pair that stores the conversation summary. Apply the assign method with message log serving as a parameter. The information we need is stored in the callable object chat memory .load memory variables. Now we can apply the invoke method with the known dictionary. Excellent! We've retrieved the initial question and the dictionary with message logs. We're now ready to feed this dictionary to the prompt template. Well, almost. Notice that the message log value is not a string with the conversation summary, but rather a dictionary. We don't want to feed the entire dictionary to the prompt template, only the string. In the next lesson, we'll show how to do this effectively. If you're still uncertain about how the assign method operates, I encourage you to watch the lesson again, play around with this function, and importantly, do the exercises following this lesson. They'll help you solidify your knowledge and confidently move forward in the course. Thanks for watching, and see you in the next lesson. Hey everyone! In the previous lesson, we explored utilizing the runnable pass-through class to append new keys to a dictionary, enabling us to store a summary of the ongoing conversation as a key-value pair. The trouble we encountered was that we stored the entire dictionary using the load memory variables method, rather than just the summary. A straightforward way of extracting the value is through the item getter method. If you're unfamiliar with this Python built-in function, item getter is shorthand for fetching items from objects that support the getItemDunder method. Common built-in data types that implement this method include lists, tuples, strings, and dictionaries. Undoubtedly, examples best illustrate this. Let's explore a few. First things first, go to the top of the last lesson's notebook and include the following. From operator, import item getter. Additionally, import the runnable lambda class right after runnable passthrough. Let's implement a toy example of retrieving the first character of a string. To do so, type item getter, select the element indexed 0, and specify the object within a second set of parentheses. I'll use the string hi, which retrieves the first character of this string. Let's test it with another object, a list, and retrieve the element indexed 2. As expected, we obtained the third element from this list. Crucially, we must test this function with a dictionary. Insert a dictionary with a single key-value pair within the second set of parentheses. Set the key to message log and the value to an empty string. Within the first set of parentheses, type the key whose value we want to retrieve. And there we have it. How convenient, right? Finally, for this example, let's wrap the item getter function inside a runnable lambda. This allows us to apply the invoke method with the dictionary passed as an argument. We retrieve the same result as before, the empty string. Importantly, this implementation allows us to use item getter as part of a chain. Let's give it a try. Copy the runnable pass-through instance we defined in the last lesson and paste it into a new cell. Note the value of the message log parameter and consider it the first component of a chain. Let me quickly rearrange the components so the chain is nice and readable. Let's now feed the output of this component as an input to an item getter function. Excellent! We've successfully set the message log key to an empty string. Once we communicate with our chatbot, this string will be populated with the conversation summary. And now we're fully prepared to feed this to the prompt template. We'll continue with this task in the next lesson, combining all building blocks to create our memory chain. Thanks for watching. Welcome back, everyone. I hope you've had the opportunity to complete the assignments preceding this lesson and are now fully prepared for this one, where we'll combine all building blocks into a single chain. If you're ready, open a fresh Jupyter notebook and let's begin. I started with a clean notebook for this lesson because the previous one became cluttered with examples. In this new one, I've prepared the following code. First, I've included the magic commands setting the API keys as environment variables. Afterward, I included the following imports. You can pause the lesson and transfer them to your notebook. Next, I've copied and pasted the definitions of the string template and the prompt template object. Finally, we have the chat and chat memory objects set up in the familiar manner. Now, rather than immediately creating the chain, let's invoke each component separately. This way we can easily trace how the chain evolves. Start by defining a variable called question to hold the frequently explored query in this course. Can you give me an interesting fact I probably didn't know about? Next, we must feed this question to the prompt template. To achieve this, we employ a runnable pass-through instance invoked with a dictionary mapping the key question with the analogous object. As a result, the input dictionary has returned unchanged. Next, we'll utilize the assign method to expand this dictionary by adding an extra key value pair with message log as the key. The value would result from the load memory variables method applied to the chat memory object. We obtain an expanded dictionary with message log also corresponding to a dictionary. To remedy this, we attach an item getter function and extract the value corresponding to the message log key. By applying these modifications to the runnable pass-through instance, we achieve the desired output. Let's assign this result to a variable called dictionary output. Then feed it as an argument to an invoke method applied to the prompt template object. The result is a string prompt value object, storing the template we defined above with all input variables filled in. For convenience, let's keep the result in a prompt value output variable. The next step in the sequence is to pass this variable as an argument to chat's invoke method. We obtain an AI message storing a response from the model. Let's re-invoke the model, this time saving the response to a variable called AI message output. The last piece in the chain is the string output parser class, which will extract the string from the content parameter. Let's store the result in the variable called response. Now that we have the result from the model, we can feed it as context to the conversation summary memory object. To do so, type chatMemory.saveContext. The saveContext method accepts two parameters, inputs and outputs. They should both be set to dictionaries, storing a single key value pair. Let's set the keys equal to input and output. Map the first key to the variable question and the second to the variable response. Run the cell. In the following one, display the memory variables of the chat memory object. we retrieve the familiar dictionary, but the value isn't an empty string this time. Instead, it's a summary of the conversation held so far. We can, therefore, go back to the top of the notebook and change the question to another one. For example, can you elaborate a bit more on this fact? Run the following cells and observe the changes. You can pause the lesson and study each output at your own pace. Once all cells are executed, the model elaborates further on its previous answer, and the message log key is now mapped to an updated conversation summary. All right, everyone, the hard work is done. All that's left is to combine these elements inside a chain. First, let's go up the notebook and rerun the cell, defining the chat memory variable to clean all memory variables. Then, return to the final cell and define a new variable called chain. For convenience, let's attach a 1 at the end of the name. Define the chain by piping together the following components: the runnable pass-through with additional keys, the prompt template, the chat object, and the string output parser. Outside the chain, define a variable called question and set it equal to the familiar one. Immediately after, set the variable response equal to the output from the chain when invoked with this question. Once the response is generated, we must save it as context to the chat memory object. Finally, display the response variable. Upon running the cell, we obtain a familiar fact. Let's test the chain with a follow-up question. The chatbot indeed remembers our conversation. As a final touch, let's apply our knowledge of decorators. To begin with, redefine the chat memory object again to clean the memory variables. Then scroll down to the end of the notebook and initiate a new function, which I'll call memory chain. Set question as a required parameter. Conveniently, we've already implemented the body of this function in the cell above, so let's copy-paste it. As Python syntax requires, we must indent the code to include it as part of the function's body. Remove the definition of the question variable because we'll later provide it as an argument. Include return response as the final line of the definition. Lastly, chain decorate this function to convert it to a runnable lambda. Looks good so far. Let's put the chain to the test by invoking it with our favorite question. Wait for a second, and indeed, we get our interesting fact. Next, provide a follow-up question. As expected, the chatbot elaborates further on its previous answer, so we've successfully created a stateful chatbot. I encourage you to add a line of code that prints out an ASCII graph and reveals the sequence of the entire chain. With that, we have a solid foundation of the LangChain Expression Language and can confidently move forward to other interesting topics. What follows is an exciting discussion on the RAG technique, which stands for Retrieval Augmented Generation. Looking forward to seeing you there.